Okay, for the lab where you're trying to identify whether you have lithium carbonate, sodium carbonate, or potassium carbonate, you need the molar masses of each of these. And so the numbers I've given you are just rough estimates. For sodium carbonate, 2 sodiums is about 46 plus 60 gives you 106. And potassiums are about 39, so 2 of those would be 78 plus 60 would be 138. So these are the numbers that you're trying to achieve. And when you look at the reaction between lithium carbonate, aqueous, plus calcium carbonate, aqueous, so I'm going to let you catch up with that real quick. You will precipitate calcium carbonate, which is a solid, and you will have 2 lithium chlorides, which will be aqueous. So the idea here is that you weigh your unknown. And it doesn't matter whether it's lithium carbonate, sodium carbonate, or potassium carbonate, you weigh it.
All right.
And then when you get the grams of calcium carbonate, because you filter it, you dry it, and then you filter it, you dry it, and then you weigh it, this mass is the difference between your empty filter paper and your filter paper with the solid in it. So you take that, turn that into moles using the molar mass of calcium carbonate, which is around 100 grams per mole. And you turn that into moles of lithium carbonate. And you take that number here, and whatever that number is, I'm going to call it X. You take X moles, divide it by your weight in grams. Oops, the other way around. You take your, we'll call this Y grams. You take your Y grams, divide it by your X moles, and you get the molar mass of your unknown. And if it matches 78, you got lithium carbonate.
Mine was 60.
So how much of this stuff did you use?
0.6 grams of calcium CaCl2.
Nope, not that. How much of this stuff did you use?
1.2.
1.2 grams?
That's with the filter paper. Sorry, I just have a bunch of numbers in front of me. I just had the answer written down. I haven't put none of this together.
Okay, so I'm going to tell you that the filter paper weighs about 1.2 grams by itself.
Right. Well, mine was my filter paper was 1.3. I had a 1.6, so it'd be, I ended up with 0.3 after everything was done.
Okay, so about 0.3. Now you should have two digits after the decimal.
My scale doesn't go that well.
Oh, you're gonna have a tougher time with this.
Yeah, I figured as much. I'd be off some, but you know, be the best you can with what you got.
So you got about you got about 0.3 grams of this, not this. How much did you use to begin with?
Not sure from my notes right now. Like I said, all I was going to do is ask you the question.
Well, you got to take that 0.3 grams and turn that into moles. And you're going to follow this pathway right here. And basically, the pathway is 0.3 divided by 100.
Okay.
And then once you get that number, you have to divide it by whatever that weighed. And you should have used, per instruction, about 0.5 to 0.7 grams.
Yep.
But you have to know how much you used, otherwise it doesn't work.
0.5 grams.
Okay, so I can just do this real quick without showing you units. Your mass is about your molar mass is like 166. Now that's a really rough calculation based on what you've given me, which would indicate that it's got to be potassium carbonate. It's not close to any of the others.
Okay, I gotta do my math again and see what happens.
Yeah.
No
Do your
problem.
math. Do your
That's what
math.
I wanted to know.
Okay. Good. Hello, everyone else. Are there any questions that you'd like to ask before we start going over some chapter 5 stuff?
Yeah, Tony, I have a question about exam 1. I just saw that you posted some of the results for mine. I'm just wondering, because I saw on Canvas that even after we took it, we can't like kind of see, how we did.
Well, the reason I don't put the exams out there for you to see all the time is because I usually use them from semester to semester. And
Okay,
it's way too much effort for me to write a new exam 4 times during the semester.
right.
And so,
So should we just email you specifically about,
Yeah,
what we got
question.
wrong?
yeah.
Okay, thank you.
Now there's 110 points possible. Whatever points you got are that much out of 100.
Okay,
So the exam is curved.
exactly. Okay,
So if you did above a 70 for your first exam, you should be happy.
right.
Well, I won't say you should be happy, but usually
Well, if you got a
average-
110 out of, or a 100 out of 110, you should be pretty happy.
if you get a 100, no, it's going to be a 100 out of 100. You see, it's 100 out
Well,
of
right, exactly, because the 100 out of 110 points is actually 100%.
Yeah, so it's almost like you did a perfect job when you didn't,
Okay, so
if that makes any sense.
I'll shoot you an email.
And so that 10 points is kind of like the curve for taking a hard test.
Right, thank you.
Okay. All right. Other questions? Okay, well, I don't want to cut anyone off. Other questions? Hello? Let's get started with some chapter 5 stuff. I will tell you this. Usually we take the second exam the last day before spring break. So that would be Friday. We're not going to do that. I'm going to let you take it Monday when we return from spring break. So you can have spring break as time to study for the second exam or not. Maybe you want to go to Cancun and hang out with Ted Cruz. I'm not sure. That was a joke, because Ted Cruz, never mind. Okay. So we're going to finish up chapter 5 this week. Tomorrow, there'll be a lab posted where you're going to watch a video and you're going to do the lab based on the video. On Thursday, you're going to do a lab where you're doing a specific heat capacity lab with your pennies and your dimes. And then spring break. So I'm also going to make the quiz due the same day, that Monday, but I'm going to make it available Sunday and Monday. So if you want to work on it Sunday, you've got all day Sunday to work on it, plus Monday to do it so that you can do well. I will change the settings so that you can see if you got answers right, but it won't tell you what the right answer is or something like that. I think I used different settings for the last exam, and I'll just change them back if I can remember. So does everyone kind of get what we're doing for the next 5 days, including today and the following Monday? Not the following Monday, but the Monday following spring break. Okay, let's have a contest. Who's going to do the most exciting thing for spring break? So silence. You guys aren't doing anything. Okay, who's going to do the coolest thing for spring break? Me. I'm going to take naps. Okay, let's get started. So you do really want to watch these lectures because when I answer these questions, I'm not going to try and give you the lecture. I'm just going to try and remind you of what was in lecture. So here, what determines the directionality of energy transfer as heat? So I'm going to give you this real quick and make sure I'm recording. Okay. So if you have a hot object, so we're talking about a high temp, and you have a cold object, a cold temp, and you bring them together so that they can exchange heat, heat always flows from the hot to the cold. And over time, what will happen to the hot object as heat flows away from it is it will become warm, and the cold object, as heat flows into it, it will become warm. And when they reach the same temp, that's called thermal equilibrium. And that's a term you definitely want to know, thermal equilibrium. Okay, now there's some other things I want to share with you about this particular idea very quickly. And those ideas are this, that there's something called the law of the conservation of energy. I'm abbreviating conservation. And the law of conservation of energy says that energy cannot be created or destroyed. What we can do is move it around. And when you move it around, you're moving around between potential and kinetic energy. And also you're moving it as kinetic energy from one thing to another, or potential energy from one thing to another. All right. So we have terms for heat flow. For instance, if you have an object and heat is flowing out of the object, so relative to this guy, we call this exothermic. Now, if you have an object and heat is flowing into it, we call this endothermic. So this is relative to this object. All right. Now, what happens when we put hot and cold together? So here's your hot, here's your cold, and energy flows from the hot to the cold. We would call this exothermic, and we would call this endothermic. Now, we also give these sign. So the sign for exothermic is negative. The sign for endothermic is positive. And you want to memorize that. Now, if heat cannot be created or destroyed, whatever this amount of heat is that's leaving the hot, it equals the amount of heat that's entering the cold. So the symbol for heat is Q. So the Q that's leaving the hot is equal but opposite in sign to the heat entering the cold. So let's say that this happened to be 10 joules. Then here, this would be negative 10 joules, and this would be positive 10 joules. Okay, because endothermic is positive and exothermic is negative. And if you take a look at these two numbers and add them together, you get 0. And this is a statement of the law of the conservation of energy, that if you take the different Q's of things that are sharing heat and you add them all up, you get 0. Okay, so that was more than you probably wanted for that one, but there you go. So I'm going to be looking to make sure that if you have any questions, you ask them. So please ask any questions now before we move on. Okay, we'll put that one off to the side. Identify whether the following processes are exothermic or endothermic. Now, I want to revisit what I just said about exothermic and endothermic. So I'm going to make a little list here. Endothermic. This is heat absorbed or into. it's positive. And the other thing I'm going to tell you is that the heat is a reactant. For exothermic, which is heat released, negative, heat is a product. Now, I'm going to tell you a really stupid joke here, so be ready to groan. Like I'm talking about a full body internal groan, like, ugh. So here we go. So even though I say that endothermic is a positive energy and exothermic is negative energy, the sign just tells you the direction the heat is flowing. There is no such thing as positive or negative energy unless you're a Buddhist. What do you think? Full body groan? Yes? All right. So the sign just tells you which way the energy is going. Let's take a look at these problems here. The reaction of sodium and chlorine. Now, if you look in your book, they actually show you this reaction. And it makes sodium chloride. And I'm going to go ahead and balance this. So there's a 2 here, there's a 2 here. There's a whole lot of energy being given off by this reaction. So if the energy is being given off, that's a product. So based on this for A, we're going to say this is exothermic because the energy is a product. For B, cooling and condensing gaseous nitrogen to form liquid nitrogen. Whenever I see a change in state problem, I like to do this. And here, I like to put a little arrow that goes up like that. So here, the reason I do that is because liquid nitrogen is more stable than gaseous nitrogen. You have to add energy to take a liquid and turn it into a gas. Now, this is a weird problem because we all know that nitrogen is a gas at room temperature, but it's a gas at room temperature because of room temperature. If it were colder, it would be a liquid. So it only happens that it's a gas at room temp because room temp is so high. So you actually have to warm liquid nitrogen to turn it into a gas. So this process is endothermic because you have to put energy into the liquid nitrogen. So this is what the reaction would look like, although it's not really a reaction, it's called a change in state. And this one, you know, might not be too familiar with what you are used to thinking about, but what you want to do is always relate it to water. Do you have to add energy to water to make it boil? And the answer is yeah. So it's the same for any liquid. To turn it into a gas, you have to have energy, so it's endothermic. Okay, letter C says cooling a soft drink from 25 to 0. So here is the same thing. We're cooling it from 25 to 0 degrees Celsius. We know this way is endothermic. So what is energy flown in the opposite direction? It's exothermic. So when you have a soft drink being cooled down, it's releasing heat. And you might be thinking to yourself, but wait a minute. When I put a soda in the refrigerator at room temperature, I don't feel any heat being given off by the soda. And in fact, you do. The refrigerator takes the heat and sends it out the back. So that's why your refrigerator is always warm. It's pulling heat out of things, making it exit, and it's releasing it. Okay, so to take your soft drink at 25 degrees Celsius and turn it into your soft drink at 0 degrees Celsius, you got to think to yourself, if you put energy here, does it make sense that the soft drink at 25 would go to 0? If you put energy into your warm soft drink, that doesn't make sense. So the energy must go over here. The energy is a product, so therefore it is exothermic. And the last example, yes,
I have a question about letter B.
yes.
It says cooling and condensing, so I'm confused why you didn't do the gas to the liquid.
Oh, you're right. Good catch. So it's exothermic.
Okay.
So it turns out that if you take a reaction like this and write it in reverse, you put N2 gas goes to N2 liquid plus energy, and that is exothermic. Thank you for catching that. And the reason you can write the reaction in reverse like this, where the reactants become the products and the products become the reactants, is because of the law of the conservation of energy. Okay, and the last one, you're going to take this mercury 2 oxide, which is a solid, and you're going to turn it into mercury, which is a liquid, and oxygen, which is a gas. And we need a 2 here and a 2 here to balance it. And it says you're going to heat it up. Is heat a reactant or a product? And the answer is the heat is a reactant, so this is endothermic. Any questions? Okay, we're going to move on. The specific heat of benzene is 1.74 joules per gram K. What is its molar heat capacity? So there's a few things I want to start off with. First of all, units of energy. Are joules and calories with a lowercase c. The abbreviations are J and calorie with a lowercase c. And you want to know that 4.184 joules is equal to 1 calorie. And this is not defined. So the one has infinite zig figs and this has 4 zig figs. The reason it's not defined is because these two scales were developed independently. And this was found to be the relationship between the two. Now, there is something called the food calorie. So 1 food calorie is 1,000 of these calories. And for a food calorie, you use an uppercase C. So a lot of people like to call this a kilocalorie because 1,000 is a kilo. So 1 food calorie is a kilocalorie. And to give you an idea of how much energy there is in 1 calorie, like this one, the chemistry calorie, if you were to pick up a 6-pack off the ground, you would expend 1 calorie. If you wanted to expend 1 kilocalorie, 1 food calorie, you'd have to pick up that 6-pack 1,000 times. So does that make it seem like a food calorie is a lot of energy? It should, because it is a tremendous amount of energy. So when you look at that Big Mac on the menu and it says 1,000 calories, that's 1,000 uppercase calories. Multiply that by 1,000, and it's really 1 million kilocalories, or 1 million calories. And that means you'd have to pick up 1 million 6-packs to deserve that Big Mac. Okay. Now, there's also the definition of the amount of a calorie. 1 calorie is the amount of energy. So this is the definition of 1 calorie. 1 calorie is the amount of energy needed to heat 1 gram of water by 1 degree Celsius. Technically, it's from 13.5 degrees Celsius to 14.5 degrees Celsius. but it's exactly 1 calorie, exactly 1 gram, exactly 1 degree Celsius, because these numbers are defined as exactly 13.5 and exactly 14.5. So that's the definition of a calorie. This here is called the specific heat capacity of water. So how do we incorporate all of this? 1 calorie, 1 gram, 1 degree Celsius. We say that the specific heat capacity of water, C, is equal to 1 calorie per gram per degree Celsius. So this is how it would be written. And this also gives you a formula for calculating specific heat capacity. Specific heat capacity is the energy. Now, remember, I told you before that we like to use Q for the energy, for heat energy. G is going to be mass, so we use an M. And this C, you can see, is a change in temp, so we use a delta T for change in temp. So this is a neat formula. A lot of people memorize this as follows. Q is equal to MCAT. This way, everything's in the numerator, and a lot of people have heard of something called the MCAT, which is something you take if you want to get into med school. So the delta looks kind of like an A, so MCAT. All right, so that's some background information. Now we have the specific heat capacity of benzene is 1.74 joules per gram K. The other thing I want to show you is we do have energy on top here, grams on the bottom, and change in temp on the bottom. The thing I want to tell you about this is that if you go from 0 degrees Celsius to 10 degrees Celsius, that's a plus 10 degree change. This number in Kelvin is 273.15 K. Well, and this one is 283.15 K, which is plus 10 K. So what I'm trying to tell you here is that the amount of change is the same, whether it's Kelvin or Celsius. So a lot of times people write 1 calorie per gram K, but that's equal to 1 calorie per gram degree Celsius. And this is one of those places where I allow you to change between K and degrees Celsius without doing a conversion. Okay? So this is going to be useful for us to know. We can do K or degrees Celsius here. All right, so let's take a look at the problem. We have 1.74 joules per gram K, and we want joules per mole K. So we want to multiply by something that has grams on the top and mole on the bottom, which looks like a molar mass. So we're going to do the molar mass of benzene. 6 carbons is 72.06. 6 hydrogens is 6.06. So you get 78.12. So 78.12 grams per mole, and we'll get our answer. And you can see that the answer is going to be not quite as much as 160 because you have 1.74, not 2. So maybe 130, 140. And we get 136 joules per gram per mole because the K or the grams, oops, I screwed that up. 136 joules per mole per K. So this is the kind of work I'd expect to see for a problem like that. Only much neater. Any questions here? Okay, we're going to move on. How much energy is required to raise the temperature of 50 mils of water from 25.52 degrees Celsius to 28.75 degrees Celsius? The density of water is 0.997 grams per milliliter. So we're going to use that formula. Q is equal to M cat. So what is the mass of water? Well, the mass is going to be 50 milliliters times 0.997 grams per milliliter. So I get 49.85 grams. I don't want to round early, so I'm going to put a little arrow pointing to the 8 saying that's where I would round if I had to. The specific heat capacity of water we've memorized as 1 calorie per gram per K. Notice when I say this, if it's in the bottom, I say a per in front of it. 1 calorie per gram per K. And for the change in temp, whenever you do a change, one of these little deltas, it's always the final minus the initial. Just like for our density lab, we did the final volume minus the initial. So in this case, we're going to have 28.75 degrees Celsius minus 25.52 degrees Celsius. And the difference is going to be 3 here, 2 here, and 3 here. 3.23 degrees Celsius. And this is good to hear because this is good to the 100th and this is good to the 100th. So this is good to the 100th. So now we can calculate the heat as 49.85 grams, little arrow there, 1 calorie per gram. And here, remember how I said we can change that to degrees Celsius, and I'm going to let you do that without doing a conversion. So I'm going to put degrees Celsius here. Now, why did I want degrees Celsius there instead of K? That's because my change in temp was in degrees Celsius. So while I'm willing to let you change these units should be the same when you see them cancel in the problem. So I get 161.0155, and the grams cancel, the degrees Celsius cancel, and we get calories. And we want to round to 3 significant figures because of this and this, which both should have 3 zig figs. And remember, the amount of a calorie is defined by the specific heat capacity of water, which is what this problem is about. So this is infinite. So we get 161 calories. And I'd expect to see all of this work for a problem like this. Okay, this time I'm going to wait for a thumbs up when you're ready for me to move on. Are you good on this, Rebecca?
Yeah.
Okay. So here we have that a copper block is absorbing 1.85 kilojoules of energy as heat. The temperature is 37. What was the initial temperature? So this is another specific heat capacity problem. Q is equal to MCAT. Now here we want to expand this and say Q is equal to MC T final minus T initial. And if we want the initial temperature, we want this on one side and everything else on the other. So it's going to look like this. So here, stepwise, I've shown you how I've isolated Ti. So T initial is going to be T final minus Q over MC. So here we need to know the final temp, which is 37 degrees Celsius. We need to know the amount of energy, which is 1.850 kilojoules. The mass is 0.500 grams or kilograms. And the specific heat capacity of copper, you have to look it up in the book. And in the book, it's 0.385 joules per degree Celsius. Okay, so let me show you some fancy footwork on this part right here. This joule cancels with that joule. This gram cancels with that gram. And this K cancels with that K. You can do that with prefixes, believe it or not. This degree Celsius, when you put it above this line, it becomes degrees Celsius to the -1. And then when you put it above this line, it becomes degrees Celsius. So I have this saying where I say, for a unit, if you cross the line, you change the sign. Well, when you do a double cross, you don't change your sign. So we plug all these numbers in and we get 1.85 divided by 0.5 and divided by 0.385. And just a real quick estimate, 0.5 will go into 1.85 between 3 and 4 times. So let's call it closer to 4. And we'll just say it goes in 4 times. 4 divided by 0.385 is about 10. So this answer here should be about 10. And I get 9.610. And this is good to there. So this is good to the ones. This is good to the hundredths. When I subtract these two, I'm only good to the ones. So my answer ends up being 27 degrees Celsius. Now, this is the work I would expect to see along with this to begin with. I don't need to see your math to isolate Ti. Now, a lot of people, they just plug the numbers in here and then solve for Ti. When I see people do that, I see more mistakes than if they do this. So does it make sense that the initial temp should be lower than the final temp when you're putting hot metal into the water? I think it does. Okay, are we good to go? You just let me know when you're good, Greg. Thank you. Okay, number 12. This is a tough one to do because we have 2 different beakers at 2 different temperatures. So one beaker, you got 156 grams of water and it's at 22 degrees Celsius. The other beaker, you got about half as much. And it's at 95 degrees Celsius. And you mix the 2 together. So when you mix the 2 together, it's going to be about here. And what is the mass going to be when you have 156 and 82, 5.2 mixed together? Well, we just add those 2 numbers together and we should get close to 250, right? And I get 241.2 grams. And when we add these 2 numbers together, since this is good to the 10th and this is good to the ones, this is only good to the ones. But I'm not going to round yet because we're not supposed to round early. Now, what will be the final temp of the 22 degrees Celsius water compared to the original temp? Will it be the same, higher, or lower? Well, I'm thinking if we mix hot water in with this temp will end up being higher than 22. And for this 85.2 grams, I'm thinking if we add cold water to this, the temperature will end up being lower than 95. So what will the final temp of this hot water be compared to the cold water over here? And the answer is they will be the same temp because of something called thermal equilibrium, where you put a hot object with a cold object, and when they exchange heat, they will both end up being the same temp. So we have T final here. Now, should the final temp be closer to 22 or should it be closer to 95? I'm thinking it'll be closer to 22 because we have more of the 22 degree water than the 95 degree water. Fair enough? So how do we solve this? Well, I'm going to call this Q of the cold, Q of the hot, and Q of the mixed waters, right? And we know that energy is going to flow from the hot to the cold water. So how much energy? Well, it doesn't matter. I do know that the amount of energy flowing out of the hot has to equal the amount of energy flowing into the Q. Now, if we look at the directionality of heat transfer, this is going to be negative and this is going to be positive. So there's something we get to use that looks like this. Q of the cold plus Q of the hot is equal to 0. Because if this is 10 joules, this would be equal to negative 10 joules. This would be equal to positive 10 joules. And we add those two together, we get 0 joules. So if you add all of the heat transfers together, you should get 0. Okay. Now, remember Q is equal to MCAT, right? So here, I'm going to change my piece of paper and I'm going to do this. I'm going to write C is equal to Q over M delta T. Now, Q of the cold water is Q of the cold water, mass of the cold water, change in temp of the cold water. C of the hot water is Q of the hot water minus mass of the hot water and change in temp of the hot water. Now, since these are both water, C of the cold water is equal to C of the hot water. So we can basically say that Q of the cold times the mass of the cold divided by the mass of the cold, change in temp of the cold, is equal to Q of the hot, mass of the hot, change in temp of the hot. Furthermore, we can say that Q of the cold is mass of the cold, T final of the cold minus T initial of the cold, Q of the hot, mass of the hot, T final of the hot minus T initial of the hot. Now you might be wondering, why did I not put an H here for T final and a C here for T final? And the answer is because they're both the same final temp. So basically now all we have here is just a big old math equation where we need to get TF on one side and everything else on the other. So I'm going to do a little cross multiplication and get MC TF minus TIC times Q of the hot is equal to Q of the cold, mass of the hot, T final minus T initial of the hot. Then I'm going to multiply everything out and get MC T final Q of the hot minus MC T initial C Q of the hot. is equal to make this look the same as this, MH T final Q of the cold minus MH T initial of the hot Q of the cold. So this is where I am so far. And you're going on a journey through algebra. It's a frightening world sometimes. Now I want to get the TFs on the same side, so I'm going to say MC TF Q of the hot minus MH TF Q of the C. So I'm pulling this to this side, and I'm going to put this on the other side. MC TIC Q of the hot minus MH TIH Q of the C. I'm going to divide out TF, and I get MC Q hot minus M hot QC is equal to all of this stuff. Oh boy, almost there, almost there. So finally we get that the T final is equal to mass of the cold, TICQ hot minus mass of the hot, TIHQC all over mass of the cold times Q of the hot minus mass of the hot, Q of the cold. And I sure hope I haven't made any mistakes along the way. So the mass of the cold was 156 grams. The initial temperature of the cold was 22 degrees Celsius. The Q of the hot, oh, I should have taken care of that. Here's how we deal with the Q of the hot. The Q of the hot is equal to negative Q of the cold, or vice versa. So I can take this and make that Q of the hot and change the sign here. Take that, make that Q of the hot, change the sign there, and get rid of all these Q's. So the mass of the hot is 85.2 grams. And the initial temperature of the hot is 95 degrees Celsius. And all this divided by the mass of the cold, 156 grams plus 85.2 grams. All right. So let's see what we get. So I get 3,432 grams degrees Celsius for that. I get 8,094 grams degrees Celsius for that. And I get 241.2 grams down here. Since this only has 2 zig figs, this is only good to there. This has 2 sig figs, that's only good to there. So I get 11526 grams degrees Celsius over 241.2 grams. The grams cancel. And this is going to be good to here. So when I add these two together, this is good to here. So I'm going to get 3 zig figs divided by 3 zig figs. So I get 3 zig figs in my answer. So I get 40 47.8 degrees Celsius is my final temp. And if we draw a little number scale here where we have 22, 95, where would 47 be? 47 would be about 50 away from 95 and about 25 away from here. So this would be about 47.8. And you can see that it is closer to the 22 degrees than it is to the 95. Now, if you can do a problem like this where it has all of that algebra, all of these different concepts, you're in a good space. This is a tough one. All right. So I'm going to go ahead and move on from this one. If you can do a problem like that, I wouldn't feel too bad. Now, 14. Can you see how this is just like the previous one? So we're going to put that one off to the side. Actually, for 14, let's take a quick look at it. What makes 14 a lot easier? And the answer is, well, let's draw it out. We have 108 grams of water at 22.5 degrees Celsius. And oops, you mix it with 65.1 grams. So here's my 65.1 grams. And we don't know the initial temperature. And when we're done, we're going to have 173.1 grams total. And T final is equal to 47.9 degrees Celsius. So I'm going to show you what makes this an easier problem is that we know the final temp. And we don't know the initial temp. So we can still do Q of the hot plus Q of the cold is equal to 0. And we can expand this guy out. So Q of the hot plus C hot, M hot, delta T hot is equal to 0. And then we get Q hot plus C hot, M hot, T final, which is 47.9, minus T initial of the hot. So this is the hot, this is the cold, is equal to 0. And this, when we do a little bit of manipulating, we get T initial of the hot is equal to Q of the hot minus specific heat capacity of the hot, mass of the hot, times T final. So I'm not going to show you step by step how I got to here. I think I did it right, and we'll just hope I did. Oh, I see one thing. I put this guy over here, that became a negative. This guy goes over there, that's a negative. So it should be positive.
Well, since it's multiplied, you'd subtract the Q of the H and you'd have to divide by C of the hot, M of the hot, and then you can add, or then you can subtract T of the F and then multiply by -1.
Yeah. You're right. So you got T initial of the hot. Are you a math major?
No, I'm studying geology though, so I have to take a lot of math classes.
Geology?
Yeah.
Okay. Why geology instead of chemistry?
Well, I'm interested in geoarchaeology. I originally studied anthropology when I went to school a long time ago, so.
Okay, I'm just knocking geology just because you always hear about rock for jocks, right? And you seem to be a pretty smart individual, which to me seems like a waste of mind. And don't let the geology teachers know that I said that.
Okay.
But then again, you know, if you're smart and you go into geology, considering that not a lot of smart people do, you're going to be cream of the crop. You know what I mean?
Thank you. I'll
Okay.
take it.
So let's go back to what you were saying here. So you get T initial of the hot is going to be, we take this over here, and I'm going to leave that as a negative for now. That's negative Q of the hot, right?
Right.
And then we're going to have to divide each by Q of the hot, M of the hot. Actually, I'm going to do this, T final minus T initial. Take this over and then divide by that. Does that look good?
Yep.
And then we'll do a negative, positive, positive on everything. And then we get T initial of the hot is T final plus Q of the hot over C of the hot, mass of the hot.
Right.
Okay, but now we got to expand this just a little bit more. And here's what I mean. We get T final is Q is C of the hot, mass of the hot, change in temp of the hot, over C of the hot, mass of the hot. So I expanded Q of the hot to be C MCAT basically.
Okay.
Are you with me there?
Yeah.
And look at these. These go away. And this should be plus, right? And this goes away.
Okay. Yeah.
And so all we have to do is put T final, which is 47.9 degrees Celsius, plus the change in temperature of the hot. Oh, crap. So now I have to, it's too late to do math. So this is T final plus the change in temperature of the hot is going to be T final minus T initial of the hot. These two do cancel. So, oh, I think I got myself into hot water. I did. You see how this comes out to play?
Well, the final plus the difference.
So actually, I'm not sure that this works. We get 2T final is equal to 2 times T initial. And T final is T initial. So I screwed up. Let's do it a different way, okay?
Okay.
So we're going to start over. And people are going to learn sometimes your first try doesn't work. So here's what we're going to do. Here's the cold, 108 grams at 22.5 degrees Celsius. And we know that the cold ends up being 47.9 degrees Celsius, right?
Right.
And it's still 108 grams. It is mixed with the hot water, but nonetheless, we can calculate Q for this because Q is equal to Cm delta T, which is 1 calorie per gram degree Celsius.
Well, the final isn't going to be 108 grams though.
Oh yeah. This 108 grams is still 108 grams afterwards.
Oh, because we're not going to add them.
No, we're just going to look just at the cold water.
Oh, okay.
Just at the cold water. They are mixed, you're right, but we're looking just at the cold. So what I'm doing is I'm finding out how much energy the cold water absorbs. This is supposed to be 47.9 degrees Celsius minus 22.5.
Okay.
And 47.9 minus 22.5 is equal to 25.4. And then times the 108. And times 1, we get 2743.2 calories. And this is a positive, which means that the cold water absorbed energy. Does that make sense when it goes to 47.9?
Yeah.
Okay. So what's going to happen with the hot water, where we have 65.1 grams, and it starts at, we don't know, and it still ends up being 65.1, but ends up at 47.9 degrees Celsius. We can do the same thing, except we do one little extra thing here, and that's this. Q of the hot plus Q of the cold is equal to 0. So Q of this hot water is equal to negative Q of the cold water, which is negative 2743.2 calories.
Right.
And we want to pause for a moment and think about that. That means that the hot water gave off that much energy to the cold water. Does that make sense?
Right. They have to be equal.
They have to be equal. And of course, what assumption are we making? There's no heat loss to the air or to the cup or anything like that.
Right. You didn't wait too much time or
Yes, exactly.
whatever.
Okay, so now we have the Q of the hot is equal to, actually, I'm going to do this. C of the hot is MCAT. Actually, no, I want to do Q of the hot. Q of the hot is MCAT. Hot, hot, hot. So Q of the hot is mass of the hot, specific heat capacity of the hot, T final of the hot minus T initial of the hot. And T final, of course, is 47.9. And now we can expand this whole darn thing. But let's do this. Let's do Q of the hot divided by mass of the hot divided by specific heat capacity of the hot is equal to T final minus T initial. Does that look good?
Yeah.
Okay, and then we get the T initial of the hot is going to be T final. I take this to the other side, it becomes negative, right?
Right.
But then this is a negative, and this is a positive, so I'm going to make this look like that. Maybe I'm doing too many steps here at one time.
I will catch up here in a sec. So I have 47.9 minus Q of the H over M of the H times C of the H equals T of the initial.
Right, so 47.9 degrees Celsius minus Q of the hot, which is negative 2743.2 calories. And the mass of the hot was 65.1 grams. And the specific heat capacity is 1 calorie per gram degree Celsius, right?
Right.
So we have to be careful here because it looks like we're going to be adding temperature to 47.9. Does it make sense that the hot water starts out at hotter than 47.9?
No.
Let's think about it. Here's
Well,
cold water. Here's your hot. Does the hot start at above 47.9 or below 47.9?
above.
Above.
Right.
And you see the negative and the negative will be a positive. So we're adding a number to that. So T initial will be hotter than 47.9.
Right.
So we like that. Okay, and I get, this is good to right here. This is good to here. This is good to here. 3 zig figs, 3 zig figs. So I get 47.9 degrees Celsius minus, or excuse me, plus 42.1 degrees Celsius. So we get a total of 89, 90.0 degrees Celsius. Look good?
Yeah.
Okay, so this one was better to tackle in 2 portions.
Now, can we do that for each one, or is it better sometimes to do the Q of the hot equals Q of the cold?
You always start off with Q1 plus Q2 plus Q3 plus Q4 dot, 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 dot is equal to 0.
Okay.
And then if you can calculate each individual Q separately, all the better.
Right. Okay. I mean, as
Yep.
long as you've memorized the Q equals MCAT,
Yes.
it's pretty
And
much.
you won't be able to memorize that because you're going to become a geologist, not a doctor. And you won't be taking the MCAT. You're going to be taking the GCAT or something. Is there a graduate exam for geology if you want to get into a master's or a PhD?
I'm not sure if there's a specific exam.
Okay.
I haven't looked into anything really past the undergrad yet.
Well, if you get into a PhD program, you're probably going to have to take the GRE.
Right.
And sometimes there are discipline-specific GREs. For chemistry, we only had to take the general GRE for most schools, not the chemistry GRE. Okay, so here we want to figure out, based on this information, what is the specific heat capacity of molybdenum. So you take your 237 gram piece of molybdenum at 100 degrees Celsius, and you drop it into your 244 grams of H2O at 10 degrees Celsius. I better raise that so that it doesn't flow over the top. So
Does the solid change like how fast the temperature will like equalize?
well, it depends. Yes, it will. Solids that give off energy pretty well are metals. Metals heat up, give off energy pretty well. Also, it depends on whether or not this is a one big piece or a bunch of smaller pieces. If
Right,
it were
with the surface area and stuff.
it'd give off energy faster because there's more surface area. So a big
So it
piece
could be like impossible to do one of these if it takes too long, if the surface area is too high and then you have to wait too long and the water gets to room temperature.
Oh, no. Actually, no.
It happens fast?
If you use a styrofoam cup here
Okay.
and you put this guy in there, if you do a little bit of stirring, it comes to temperature in about maybe half a minute or a minute.
Oh, wow.
That fast. Okay. And if you want evidence of that, just think about if you take a hot frying pan and put it in the sink and you put water in it immediately, how long does it take to cool down?
Oh, it's pretty quick.
It's really quick. And it's the same thing here.
Okay.
Okay, so here we still have 237 grams. And here we still have 244 grams. But our final temp is 15.3 degrees Celsius, right?
Right.
So this one I'm going to do the whole Q of the molybdenum plus Q of the water is equal to 0, assuming there's no energy given off to the air or to the cup or anything like that. So the Q of the molybdenum is equal to negative Q of the water. C of the molybdenum, mass of the molybdenum, change in T of the molybdenum is equal to negative Q of the water. And specific heat capacity of the molybdenum is equal to negative Q of the water over the mass of the molybdenum, change in temp of the molybdenum. And then when we expand this, we get, for negative Q of the water, negative specific heat capacity of the water, mass of the water, change in temp of the water, over mass of the molybdenum, change in temp of the molybdenum. So this is one where it's probably easier just to combine the two together and get this nice little equation.
Okay.
So the specific heat capacity of water, 1 calorie per gram degree Celsius. The mass of the water, 244 grams. Change in temp of the water, it's going to be from 10 to 15.3, which is 5.3 degrees Celsius, right?
Right.
15.3 minus 10.
Yeah.
And here you can see why we really shouldn't get 5.3, we really get 5, right?
Yeah, because of one sig fig.
It's only good to the ones, and this is good to the 10th, so you round to the ones. So I'm going to put a little arrow there saying, you know what, when I do this multiplication, I get 1 zig fig. Mass of the molybdenum is 237 grams. And the change in temp of the molybdenum is going to be 15.3 degrees Celsius minus 100 degrees Celsius. And I remember it's always final minus initial, and the final is 15, the initial's 100.
Right.
Which we like because this number will be negative, right?
Which means it's an exo.
Yeah, if the temperature lowers, you're giving off heat. But the reason I like this negative is because I have this negative here, right?
Yeah.
And so my specific heat capacity will be positive, which it should be. So now we just plug our numbers in. 244 times 5.3 divided by 237 and divided by, this is going to be 84.7. Does that seem right?
Yeah.
So I get 0.06. And let's take a look at what happens with our units. The grams cancel. This degree cancels with these. And we get calories per gram degree Celsius because none of these cancel. And that kind of makes sense, right? Because wouldn't the mass unit cancel with the mass unit in this above equation?
Right.
And the change in temp would cancel with the change in temp.
Right.
So we're left with the same units as specific heat capacity of water, which is that. So it'd be nice to see all of this type of stuff for your answer, but you don't need to do the drawing. The drawing is just to understand what's going on.
Okay. So it's really nice when they give you the temperatures.
Yes. When they give you temperatures, it's all gravy.
Right.
Okay. What time is it? It's 7:18. We'll probably call it quits here. I think this one is actually done on another Q&A.
Okay.
And unfortunately in that Q&A, I forgot to record until I probably got to this one. So it actually would complement this Q&A perfectly.
Was it from one earlier today or from last semester?
The Q&A?
Yeah.
They're all from this semester. The old ones I've never published. Maybe I should if you guys want to watch them, but that's a lot of Q&A.
No, I think it's too much.
Yeah, I'm just trying to put the ones up for this semester.
It's just from this morning then?
Yeah, just from this morning.
Okay.
No one called in at noon, so I didn't do anything. All right, I'm going to do a little pause here.